So our next speaker is Hugh Balls, who is a lead developer and researcher at Studio Gobo, based in sunny Brighton, UK, which most recently created Rise Against the Empire playset for Disney Infinity 3.0. Prior to joining Gobo, he has previously worked at Disney Research and Disney Interactive Black Rock Studios on a number of graphics-related projects. His professional interests include real-time rendering, a number of areas of animation, and gameplay, design, and programming. His co-author is Daniel Zimmerman, who works at Studio Gobo in Zurich as a research scientist and engineer. He's interested in all sorts of real-time applications, in particular in rendering and interactive animation approaches. He was leading the research and development of the AT-AT and AT-ST walkers in Disney Infinity 3.0, for which he implemented and extended novel physics-based animation techniques. For Disney Infinity 1.0, he was a part of the team that developed new techniques for ocean rendering. Before joining Gobo, he worked with Disney Research on physics-based control for simulated characters. He will be presenting their topic.
Okay, so thanks very much, Natasha, and thank you very much for attending. So I was very excited during Sebastian's excellent volume rendering talk this morning, where he raised the sampling of volumes as something that needs more research. So this is a topic of our research. So I went off the script, so I need to find out where I am now. So we're going to cover a lot of ground in this talk. And we'll go through things quite quickly, but we're going to illustrate everything very visually. And we have a lot more information in the slides that you can get later, and we're going to have the full source code for everything available online. So I guess I don't really need to explain what ray marching is, but I have a very quick explanation. So for our pixel ray, we're just going to march through the volume and sample the lighting at each point. Now, that's all I'm going to say about ray march volume rendering, because everything we are presenting today is completely orthogonal to the ray march implementation or algorithm. We're only concerned with how these samples are placed and how they move with the camera. So we can achieve high quality results with a small number of samples. We've seen even higher quality results in some of the talks today. But what's the catch? The catch is that this only works as stationary or slow-moving cameras. So in this video, the camera is moving forwards at only a moderate speed, and there is a strong aliasing appearing as a flickering or boiling effect. This is happening because the camera is undersampled in the forward direction. The sample count is low, as we've seen in the other two talks today, because of the expense of shading. So instead of just doing one shading computation for the surface, we're having to do multiple in the volume. So in our research, we assume that low sample counts are a given, and we ask if there's anything we can do to reduce this aliasing. We're going to show that we can manipulate the sample layout and motion to substantially reduce this error. And as mentioned, our ideas are we're also going to describe how to adaptively sample the depth along the rays so that we can render a large range while maintaining quality near the viewer. And as mentioned, our ideas are completely independent of the algorithm or implementation. So to understand this, we're going to study the following diagram. This is a top-down view of a camera frustum, and as the rays march up the screen, will represent the collection of all the samples for all the pixel rays with these horizontal lines. So that is each ray march step. The problem is, as the camera moves, it drags these slices along with the camera. In this talk, we're going to introduce a family of methods that combat the motion of samples in the volume. We're going to refer to them collectively as pinning, as if to pin the samples in place in the volume. So for the forward motion case, there's actually a really simple fix for this, and we can illustrate this with this video. So instead of just ray marching from the camera, starting at the same position every time and walking out at the same steps, we simply offset the start position, or the start ray march step distance. Doing that, we compensate for the camera forward motion, and our samples are completely stationary in the volume. So all we need to do is integrate the camera forward motion, adjust the ray march start distance in the shader, and that's it. So it's very simple, it's more or less free, it's very easy to implement. But what about other kinds of camera motion? So let's look at strafing motion first. Again, we're in a pretty good place here. Although the samples are moving through the world with the camera, they're moving parallel to these kind of sample slices. And these are densely dampened directions through the volume. So although the samples are moving, you don't see it. However, we run into trouble under camera rotation. So there is noticeable aliasing at the sides of the view. Why does this occur? Well, for samples at the sides of the frustum, there is a significant component of the motion of the samples as the camera rotates that is off the sample slices. So the samples are no longer following these densely sampled sample slices. So there is a way we can fix this. We could just take all our rays and just scale down the rays at the sides of the screen. And then we get this curved layout. And now we can see that our sample slices lay on these kind of rotational isolines around the camera. And now the motion of the samples will be completely parallel to the sample slices, and the aliasing disappears for this case. But we're not done yet. So just to reiterate this, because the next section of our talk relies on this heavily, if the samples are moving through the world, but they're moving parallel to the sample slices, we're in good shape. But if the sample slices are moving orthogonal in that direction, we're getting aliasing. So we just showed two examples where we could address either rotation or strafing. Unfortunately, we can't have both, so it seems like we have to adopt one or the other. We spent some time looking at doing a dynamic optimization, which looked at how the camera was moving every frame and then adjusted the sample layout. But the very act of changing the layout of the samples causes them to move in the volume, so you get aliasing. So it's a kind of catch-22 situation. We did find that for some simple camera motions, a fixed in-between configuration may work. So let's say you interpolate 50% between a curved and the strafing-friendly layout. And that's definitely worth trying as a first step because it's just very simple and easy to try. But for more general camera motion, such as an interactive application where the camera is not constrained and user-controlled, we weren't able to find a satisfactory solution with these methods so far. So we asked the question, can we find a more general approach? As discussed, we want the samples to always move along the slices. Can we enforce that so it's always happening? So this animation will illustrate our approach. Here, we have these two little red spheres, and these are going to act just as stationary reference points. They don't do anything in an algorithm, they're just for illustration here. So we've already seen that for camera strafing, we're looking good. The sample slices, they don't change when the camera moves, and there's no motion of them in the frustum, they're stationary. Now let's start to transition to a rotation. And here you see that instead of moving the sample slices through the world, they're kind of extended as the camera rotates. So we've smoothly transitioned to a rotation-friendly layout. And we can add another pin and just verify that the sample slice is not moving in the world and the samples are only moving along the slice. So now we're in a rotation-friendly layout. And we can verify with our pins that we are in fact in the correct layout. And then we're going to transition back into a strafing motion. So let's move our pins over to check that the sample slice is not moving. And we get this smooth transition out of that layout. So now to see this in motion with a render. So you wouldn't expect this to work. I mean, we didn't, to be honest. I still can't believe it works. But we will have full source code available so you can actually check. So previously, when we were talking about the kind of curvature of the layout, we had a single parameter to control how the sample slices were shaped. But now we've relaxed the scales for these rays, so we can have any kind of scaling that we want. And we can use this to hold the sample size stationary. We're doing everything in flatland 2D. We think it can generalize to 3D, but we don't address that in this work. So how do we actually make this happen? Well, you can sort of see intuitively how it works from those animations, but we call this process advection, and what's going to happen is when the camera moves, we're going to adjust the scales across the screen in such a way to try and hold that sample slice stationary. It's not trivial to do. This slice is defined by like an array of scales. It's data-driven, and we need to do some kind of search. We can get overlaps and folds and this kind of thing as well. So we use fixed-point iteration to solve this. It's an iterative technique, just like the Newton method. It only requires that you define a forward mapping, which means how will the sample slice that I currently have move with the camera over the next frame. And then you just plug it into fixed-point iteration, and it just inverts your mapping. And we wrote an entire paper about using fixed-point iteration for this kinds of tasks, so you can see the references for that. So just to look one more time at the advection quickly. So let's say that our camera is moving to the left. We want our sample slices to stay stationary, so we want to shift all the scales to the right to compensate for the camera motion, which we do something like that. So what kind of issues can we run into? Well, we don't want to have high gradients in this sample slice, because then we're getting like really different scales for neighboring rays. And this will produce this kind of pinching in the render, which you can see here. It's kind of like a change in the frequency content of the render. To address this, we implemented this simple gradient relaxation approach. And all we do is we simply just push down the gradients every frame. Notice here that we're breaking our rule about not moving the sample slice and keeping it completely stationary. So there's a trade-off to be found here. Camera motion can help to hide the aliasing, so we ramp down the camera relaxation process when the camera is stationary. There's another issue, though, that's a little bit trickier, and this is with twisting of the sample slices. So if we rotate the camera in such a way that it orbits the place where we're doing the advection calculation, the algorithm's working perfectly well, and this is like a great success because this sample slice is not moving, but this is directly conflicting with our goal of not having these high gradients in our ray scales. So we address this by clamping the scales. Unfortunately, we're going to end up just pushing the sample slice around at a certain point, but this feels like a fundamental problem, and we don't have a solution for this, but maybe there is a better solution. And lastly, a quick comment about the advection. It does depend on where you do it from the camera, but we found that we didn't need to do it many times. We just needed to do it once at the far distance and once at the near distance, and then interpolate the two when ray marching. So to summarize this pinning approaches, pinning the forward motion is free and improves the results dramatically. Choosing a fixed sample curvature with that one parameter may work in particular scenarios. For a more powerful method, the advection-based sampling is best suited. So next we look at supporting arbitrary sample distribution. So instead of ray marching uniformly along the ray, we're going to have an adaptive distribution of these kind of ray samples. And note that we want to support everything that we've discussed up until now. So why would we want to do this? Well, uniform sampling can be efficient. Maybe you'll have either a short range or a low resolution near the viewer. And ideally would have the best of both worlds, would have the detail near the viewer and without compromising the range. So we're going to define a density curve which dictates the sampling density. So it's high near the viewer and low in the distance. And we use a curve like 1 over z. but anything can be used. And as I mentioned, we want to support the techniques that we've discussed so far. This is easy for a uniform sampling. When the camera moves forward, we just need to pull the samples backwards, and we just keep rolling them as you go. But it's trickier for adaptive. If we just start pulling the samples in towards the viewer, our samples start just running off the end of the ray, and we run out of samples. So what's happening here? So we found a solution for this, and it looks like the following. So if you look at this carefully, you can see that we have the sparse sampling in the far field, the dense sampling near the viewer, but we also have the samples moving, so we're compensating for the motion. And if you look carefully, you can see that we're kind of introducing samples as they approach the viewer to introduce the density. To understand how this works, we can study the following diagram, captured from an actual implementation of the sampling on Shader Toy, and you can see the side notes for a link to the shader and experiment with it. The density curve is shown in red, and the possible sample positions are the black lines. And we've drawn these lines in such a way that intersecting the density curve with the lines produces our sampling. So you can see that there are dense samples on the left, because the curve is intersecting a lot of lines, and a sparse sampling on the right, further from the viewer. And as the curve reaches the bottom of the black lines, we fade out the samples. So why would we want to go to all this trouble to take the samples? We can see that under motion, you can see that the samples are fading out, and they're moving exactly how we want them to do. So we've achieved exactly what we wanted. So we're not going to go into a lot more detail about how that works, but as I said, we have a Shader Toy shader that you can play with. So our algorithm is basically to walk along the power of two positions and blend in samples based on this density curve that we defined. We do this once for all of the rays, and we end up with sample slice distances and weights, and we can compute these on the CPU and just pass them into the shader. And then to support everything else with the advection that we discussed, we'll just scale the rays afterwards. So it's similar to before. Instead of just doing a uniform ray march, we're now doing an adaptive ray march, and then we'll scale it to get the slice configurations that we want. So what does this give us? It gives us a non-uniform distribution of samples that's completely temporally coherent. And there's an interesting question. Because this is a simple sampling algorithm, could we compute this during ray march, which raises questions about perhaps doing real-time importance sampling per pixel. But we don't follow this direction any further yet, but we leave it as future work. So we authored this kind of quick camera animation that turned out to be this really crazy, challenging use case. There's a lot of twisting going on at this point. And it doesn't look like it, but the camera's moving quite fast. But we'll see this next. And you can see the two advection lines. So we're doing the computation of the sample layout. We're doing it once close to the camera and once in the distance. So this is what it looks like doing nothing. This is just naive ray marching. And yeah, we see, as before, we get a lot of noise as the samples move through the world. And sometimes on the camera strafing it looks okay, but then whenever the camera rotates it breaks down. So now we're going to look at the case with just the forward pinning, which means just sliding the samples towards the camera when the camera moves forward, but not doing anything else. So this already makes a pretty big difference. It still breaks down, however, when the camera rotates. I don't know how well you guys can see that, but you will see some aliasing at the sides of the view as the camera is rotating. I'll play it one more time if I can. Yep. And so this is the full crazy advection approach. So we do still see some aliasing if we look really hard. We think this can be further improved with more time to settle the implementation and polish it. It's come together at a very high velocity, I have to admit. Or perhaps with future research. We'll note, however, that this is a really challenging camera animation. The volume's really undersampled, and the clouds are really stationary, so some motion in the clouds might already help to mask some of the aliasing. But in any case, our techniques that were presented have improved the result dramatically. So to summarize, we've introduced a number of practical improvements to standard ray marching. We're basically taking advantage of degrees of freedom that haven't been used up until now about how we actually do the ray marching. We also introduce a general sampler algorithm that enables a non-uniform sampling. And our approaches are orthogonal to the ray marching algorithm and easily retrofitted to existing ray marchers. And some quick acknowledgements. Shout out to Shader Toy and 2 particular shaders on Shader Toy, which we borrowed a lot from for our result. And that's it. Thank you very much.
Please come to the microphone.
Hi. I was just wondering, is there anything that prevented you from just pinning in world space so that then, like if you had a grid or something of pinned lines that you could trace through? Because that seems like that would avoid the issues with having to change the locations.
Yeah, absolutely. That's a really good point. I think the main constraint is that we need to do this officially in the GPU, and we need to kind of do this gather process. And our samples have to lie on the pixel rays. So if we did have a bunch of volume samples that were kind of defined in the world, we'd need a really fast way of kind of like integrating them all.
Oh, or I meant having like planes, sort of, so that you'd send a ray and it would hit the planes where it's as opposed to individual samples.
Yeah, possibly. I think our approaches just apply to any ray marching, so it could be used also for volumetric shadows or anything for different cases. But presumably you could set up a whole bunch of like planes to render a similar effect, I guess.
Okay.
I couldn't quite tell, but do you think the algorithm scales to adjacent edge blended fields of view? If you had to do like a 360 view of something, could it extend to that case?
Oh, like a 360 projection. I'm going to say yes, but we could discuss it later maybe. I'm not 100% sure. It's a cool idea though.
Thank you.
Hello. It appears that that if you have the same camera viewpoint, but you came from a different path, you might be sampling different places. Are there assets or scenarios where the fact that you might get a different image would be a concern?
Oh, yeah, absolutely. So I think this is very much a real-time technique. Yeah, I don't think I could sell this to film. Definitely not. No.
Tempted to. Well, let's thank you for this talk. He's not leaving anywhere yet.